In this lecture, we're partly in Chapter 17 of the Galani book. I call it Part 1 of Chapter 17. I think Chapter 17 should probably be broke into some different organization and possibly made 2 chapters, but I didn't write the textbook and don't intend to. We're just going to talk about an introduction to topography and contours. A whole lot of what land surveyors produce are topographic maps, which include contour lines. And in recent years, especially with the advent of software, contour lines are not what they used to be. They don't look quite the same, and often you can see that software is set up and produces contours according to an algorithm immensely faster than humans can, which we will do some contour interpolation soon, which will help you understand how they're generated and put on maps. But the laws of contours get broken, and it's sad when you see a topographic map put out and sealed by a professional land surveyor that does not comport to the rules of contours. And there's really no set guide rule of contours. I went back and looked at my textbook from 1988. They have some. I believe we had a handout that I cannot find that had 8 or 10 rules. I wrote my own for this course and for this module to be a good guide for topographic mapping, and it's a very broad topic. As a matter of fact, we had a class when I was a Southern Tech student over 30 years ago that was topographic mapping, and that's all we did was collect contours, use data collectors, shoot inverts of pipes, and learn how to make a good, high quality, professional level map, not just an introduction like we're doing in this class. Most of you in this class are engineering majors at Kennesaw State, not so much at UNG, and you'll be dealing with contours in work products that have been prepared by or generated by other people or other agencies. And if you don't really understand what the contour map is telling you, you will be severely handicapped in trying to turn out a good sound design. So understanding topography and contours is very important. Rules of contours. They are like the laws of physics and the laws of nature, only way cooler. Now, that's spoken by a surveyor. Everybody might not agree with me. Now, we're going to go through the 16 rules that I have prepared, and then we will look at some illustrations, and then we'll recap with these same 16 rules. A contour line is a connection of infinite points that lie at the same elevation on the face of the earth. So if the ocean were to raise to a certain elevation, that contour line would be the shore. Now, we're not talking about global flooding, but just to put it into perspective, the ocean or a lake or a pond, if you envision contour lines, that is an infinite set of points that are at the same elevation on the face of the earth, and water will rise minus any wave action, and when the water gets to that certain elevation, that's where the contour line lies. So that's a good way to visualize what a contour line is. Contour maps are drawn to different intervals. Those contour intervals vary according to the purpose. When we first look at a contour map, we will typically see that every 5th contour is an index contour, and it will usually be darker or a different color or somehow set forth from the other 4 intermediate contours. So for example, if the contour lines are drawn at a 1-foot contour interval, where you go from 941 to 942 to 943 to 944, 940 and 945, as well as 950 and 955 are index contours. The ones in between, the 1, 2, 3, 4, 6, 7, 8, 9 contours are intermediate contours. And if you look at a big scale, like a map like a USGS topographic quadrangle map, the contour interval may be 20 feet, and so the index contours will be on the hundreds. Every contour must close on itself, even if it does so outside of the mapped area. So contour line just go up, may just end. It does not end within your mapped area. It will end at the extent of your contours. So contour lines don't just peter out and die. They keep going and around each other, because basically if you're above ground and above sea level, and even if you're below with index contours, your contour line will go back around, just like it was, exaggerate the concept for our continent is a volcano and we're way up here. That contour line is going to go all the way around the volcano. Our continent is just different, and it has lots of different hills and valleys. Contour lines do not intersect or cross because no one point can lie at two elevations. Think about it. This is true except in the rare instance of a negative slope cliff face, where there's actually a lower contour underneath the higher contour where there is an outcropping. But in a truly vertical face, the contour lines will stack or coincide. They'll all come together and they'll be the same, and then they'll come back out on the other side. Vertical face may be a retaining wall, a cut slope, the pit of a rock quarry that's blasted out of solid rock. Those are the sort of instances that would be a true vertical face. Number 5, closed contours that form circular or irregular ellipse type shapes may be hills or knolls if the elevations increase into the middle of the shape. If the elevations decrease into the middle of the shape, it represents a depression or a crater. Contour lines and depressions are usually indicated by hatching or tick marks. The term is actually hatcher without a T. 6, tops of hills and bottoms of depressions generally do not coincide with the elevation of a contour line. Thus, we know by inference that the high point or the low point is less than one contour interval higher in a hill or lower in a depression than the last contour interval drawn. 7, steepness of slope is indicated by the horizontal distances between contour lines. The closer they are, the steeper the ground is. The farther apart they are, the flatter it is. 8, where contour lines do not adequately depict elevation data, or where contour intervals are so great that they give a false impression of the ground surface, spot elevations should be provided. In valleys, ditches, and streams, aka drainage channels or drainage ways, contour lines will make a V shape pointing upstream. In the reverse, along ridges or crests, contour lines will make a V shape pointing downhill. 11, the scale of the map should be planned with the end use in mind. Number 12, non-contour features should be located with the appropriate precision and stated on the map. 13, inverts, meaning the bottom of the pipe on the inside of the pipe, of storm drainage or sanitary sewer lines should be obtained and stated on topographic surveys. Finished floor elevation of any structure within the project should be obtained and stated, as well as the corners of any flat surfaces of importance, such as along loading docks, handicap ramps, concrete pads, etc. Greater attention should be paid to contours along break lines than open grid coverage in obtaining raw topographic field data. We'll talk about that more in the next module. Points located should be spaced such that the ground between them roughly constitute a plane, or at most a deviation of 1/2 of the contour interval saw. This also will be covered in the next module. From 17.2a, this is a plan view of contour lines here in the middle, and then you have profile views of each side. I think this is a pretty good illustration. These are contour lines here, 10, 20, 30, 40, 50. Now, they did not make the 50 bolder like they should have as an index contour. Shame on them. And they've depicted points A, B, C, D, E, A, B, C, D, E, and this hill is ironically symmetrical because the same points go back down the other side. But basically, if you take a cutaway or cross-section view from point D to point F and look at it over here, then, you know, at the elevation 10, it's where these contour lines would cross. And this is what a cutaway view at D to F would look like. Now, where I kind of differ with them is, I guess we've got a spot elevation of 60, so it goes right up to 60 and stops, which is a very rare instance, as we had just covered. Likewise, over here, A, B, C, D coming up, we cut it lengthwise with this as a cross section from A to C. You see you come up gradually, and then it gets a little steeper over here and comes back down. These cutaway views help to illustrate, because these are basically the contour intervals inside the hill. So this illustrates a hill. You can see the contour lines go up, and that is actually what I would call a knoll. Figure 17.7 are coordinate squares. I would call them grids. This is where you would take topographic data shots at these grid points, and we'll talk about that more in the next module or two. But then you can see the 725 contour, the 730 contour, the 735 contour, 740, and so forth. Looks like the northwest corner of Georgia, doesn't it? These are index contours on a USGS quadrangle map. And here, these are 40-foot contours. How do we know? Because there are 4 of them. 1, 2, 3, 4. Between the index contours, which are darker, the higher one is 5,600, the lower one is 5,400. So there are 200 feet between them. 200 divided by 5 is 40. So these are 40-foot contour intervals. And so we would know by inference, with that in mind, if you were asked, like you will be on the FS exam, what is the elevation of a point right here? Well, that would be 5,400 minus 40 would be 5,360. Drop down another contour line would be 5,320. Likewise, what is the elevation of this index contour? Well, it's 200 feet higher than the next one below, so this would be 5,800 would be the elevation of this index contour. These are the sort of questions that you would be asked on the FS exam. Similarly, over here, this would be the 5,600. And also similarly, you might be asked, what is the elevation right here? Well, that's in between contours. That's where we will interpolate. You might say, okay, well, right there is a straight line between 2 contours. That would be the midpoint. So we're about 1/4 of the way down. So this being the 5,360, 1/4 of the way of 40 would be 10. So this would be roughly 5,350 right here at this point, if that is what we were asked. This is another illustration of 20-foot contour intervals on a hill. Here we don't have the elevation at the top of the hill. It's probably right in here. And let's use a different color. So they've got the index contours labeled in red and with the bolder line, and then the 20-foot contours in between, 2020, 2040, 2060, 2080, 300. So we can pretty much assume that if we were to project this profile out, the high point is probably right where I've made this green dot. Now, we know it's higher than 300 because we see the 300 contour. We also know that it's lower than 320 because if it was 320 or higher, there would be a 320 contour. So we know that the green point, the peak of the knoll, is somewhere between 300 and 320 in elevation. Now, if this is your map, you should collected a hard shot or have data generated remotely, which we'll discuss right here at the top, and just go ahead and tell everybody that's 316.5. Now you know. That may be very important. Depression contours. Again, we talked about this. There are hatchers. This is drawn correctly, nicely. We see the 80 contour out here. That's the big one. And these hatchers or tick marks are pointing downhill. So you never see these on a upland slope, well-drained area. Only when you're in a depression. In other words, the water is draining to an area that either doesn't drain out which is rare, but it does happen in some geological areas. Or there might be a pipe right here in the middle where the water collects and drains off. You have depression contours in almost every ditch line. That's usually so given that we don't depict it that way. But on a broader map where it's not that obvious, contour lines would be hatched or tick marked. And here you've got the the 80 contour, and then the 60 contour, and then the bottom is right here where this X mark is. And this, they're telling us that it's 45.7. We know it's between 60 and 40 because if it was lower than 40, we would have another contour line in here, but we don't. So we're going to go over them again. Contour line is a connection of infinite points at the same elevation. Index contours are every fifth contour. If they're 1 foot contours, then it's the fives. If it's 20 foot contours, then it's the hundreds. If it's 40 foot contours, it's the 200s. Every contour closes on itself, even if it does so outside of the mapped area. Contour lines do not intersect or cross except at vertical faces or negative slope cliffs. Contours forming circular shapes like we looked at will be hills or knolls. Those are synonyms. If the elevations increase into the middle of the shape, if the elevations decrease into the middle of the shape, like our last diagram, it represents depressions or craters, and those contour lines are indicated by hatching or tick marks. Tops of hills and bottoms of depressions generally do not coincide with an elevation of a contour line. Thus, we know by inference that that high or low point lies within one contour interval higher or lower than the last one drawn. Steepness is indicated by the horizontal distances between the contour lines. The closer they are, the steeper it is, the farther apart they are, the flatter they are. Where contour lines do not really depict elevation data well, or where they give the false impression, then we need to give spot elevations like we saw there on that hill or in that depression. Valleys, streams, ditches, aka drainage channels, drainage features, contour lines will make a V shape and they will point upstream. Along ridges where it's the reverse, contour lines will point downhill. The mapping skill should be planned with the end use of the map in mind. What we mean by that is if we're mapping a city on one sheet, then it needs to be 1 inch equals 1,000 feet or 1 inch equals 2,000 feet, and the contour intervals need to be 10 or 20 or 40 feet according to how steep the terrain is, so that the contour lines do not just become one big blob. In other words, a 1 foot contour map of Denver, Colorado would be a solid map at a large scale, like 1 inch equals 1,000. Now, 1 inch equals 20 might make a whole lot of sense if you're doing some real intricate, detailed design work. Number 12, non-contour features should be located with appropriate precision as stated on the map. These are some of the features that we're talking about that are important, such as inverts of storm drainage or sanitary pipes, finished floor elevations. Those things should always be added because you need it if you're going to add on to a building or tear down a building and build a new one or whatever. You need to know the elevation that the floor elevation is at, whether if it's an elevated floor or a slab floor. And 15 and 16 we'll talk about more in the next module. Please read the handout, take a look at some contours and topographic maps, and apply these 16 rules and make sure that you understand them, and we'll go further next time. Thank you.